Hello, I welcome you all to this another interesting screencast. The problem reads, if the spring is unstretched when theta is equal to 30 degrees, the mass of the cylinder is 25 kg and the mechanism is in equilibrium when theta is equal to 45 degrees. Determine the stiffness K of the spring. Rod AB slides freely through the collar at A, neglect the mass of the rods. So we are going to use the virtual work method. This is an alternative to the equilibrium method, equilibrium of a particle, equilibrium of a rigid body, equilibrium of interconnected rigid body. So if this is an alternative, it means you can solve this particular problem by using the equilibrium method and still find the same answer that we're going to find using this virtual work method. And this one basically states that the total virtual work in a system is equal to 0. Okay, and this virtual work can be due to the product of a force and translation of virtual displacement. It can also be due to couple moment, product of couple moment, and rotational virtual displacement. And when we sum up all the virtual work in a system is equal to 0. So given a force F and the virtual displacement del R, for virtual work to exist, both of them have to be collinear or parallel, and if they're in the same direction, then we have positive virtual work, otherwise we have negative. And the same for couple moment M and rotation of virtual displacement del theta. The two must be collinear or parallel, and if the two are in the same direction, then we have positive virtual work, otherwise we have negative virtual work. So in a nutshell, that is what virtual work is. So to start with, here let's draw the free body diagram. So at C we expect a reaction force. Draw a free body diagram. So at this particular pin there, we'll have a reaction force like so, and another one like so, and then let's make a section here. Make a section there like so. Okay, there like so. Also we make a section there. All right. Of course, down here you expect this is the weight. This is just the weight. This is the weight of this particular load. We have been given already the mass, we just need to convert it to weight. And then this part here, there's a collar here at A, and this rod is free to move. It can move in this direction or it can move in this direction. All right. And of course, we do have a spring there. So depending on which direction you move, it's either the spring will cause it to go in the opposite direction. All right. So let's section it there so that we have the spring force like so. Of course, we expect a spring force in this direction like that. A spring force like so. Okay, and another value like so. Right. Let's label this. So we have W. We have W. You'll have Fs. You have Fs, and then you have this one is Cx. You have Cy. All right. So let's say we have an angle here. We have an angle here. Let's say we have an angle there. Let's call this angle there phi. We call it phi. We call this angle phi. Therefore, we expect to have components. We expect to have components of this force F, this spring force, in this direction like so. Okay, so expect to have a component in this direction and another component in this direction. Right. So let's label everything. Of course, we've labeled that. We label this also. So this we just call it Fs. This is Fs sine phi, and this one is Fs cos phi. And this angle is similar to that one there. Okay, great. For now, this information is enough. So what we are going to do now is to apply some kind of a virtual displacement. So we are going to apply a virtual displacement, a rotational. I'm going to apply a rotational virtual displacement at A. You can apply virtual displacement at B, at A. It's really up to you, or at B, at A, or at C. So I apply myself a rotational at C. So I'll rotate this maybe by this angle like so. This angle there, it is just my del. This is my del. I'll call it as just del del theta theta c, which is just equal to del theta. Okay, so let's draw this system that is rotated. I'll exaggerate it a little bit. Okay, I'll make it just a little bit short. Okay, so let's say, of course, this member will remain the way it is, like so. So let's imagine it has rotated up to somewhere there. Okay, and then point A will just rotate a little bit. You see point A will just rotate, let's say like so. We just rotate something like so. Okay, so look at what has happened. We applied that virtual displacement at C, so we expect some movements at B. At B we are going to have some movements. We have some movements in this direction like so. We also have some movements in this direction like so. Can you see that? Great. So let's define that, this and this. Okay, great. We define that. So those are the virtual displacements that we are going to have at that particular point. So we have a movement down, and so movement down and to the right. So at B, this is what we have at B. I'll write it here. At B, we have a point moving down like so. We have this vector displacement like so. So if this is B here, this point, if this is B, let's put this as our B. So we have such movements at B. We have a movement in this direction like so. Okay, and the movement in this direction like so. Okay, right? Okay, so that is the kind of movement. So let's label this. We label this. So this we are just going to call it. I clean it a little bit. Let's label it now. So this we're just going to call it. This is just this is del. This is movement down. This is del YB. Okay, del YB. Del YB. And then this one is del XB. All right. Right, let's now pick the reference. Let me just add a few details just here. Yes, all right. Before we do so, let me just redraw this once more again somewhere here. Let me redraw this, something like this. Okay, something like so. something like so. Great. Here we go. So let's call this A. This is, no, that's not A. This is B. This is A. This is C. This is theta, and we call this phi. And this length here, we are just going to call it this length, and then we have this length here, like so. Let's call this as LAB. Let's call this one as this is 0.45, and then this one here is already given. It is 0.6. Okay, great. So let's choose our reference. We choose our reference. Let C be the fixed ref. Okay, be the fixed ref, right? Okay, so if that's the case, let's define the position B with respect to C. So we have this length from there like so, to the point C, which is there. Let me draw this like this. All right, just clean it up a little bit. I clean it up like so, and then I define this other point here, from here to here. This is in the horizontal direction. Just clean it up a little bit. Great. Let's label it. So this is XB, and this is YB. Oh, great. I think we've done the definition. Let's calculate the value of W. W is equal to 25 kgs times 9.81. This is just going to be equal to, that's 25 by 9.81. This is 245.25 newtons. Let's define Fs. Fs is just equal to K times S, K being the spring constant and S being the stretch. And we know that our S will just be equal to L final minus L original. All right. So let's calculate LAB. LAB, we are going to use the cosine rule. This is just going to be equal to, this one is going to be equal to, let's do the calculation. There we go. This one is going to be equal to 0.45 squared plus 0.6 squared minus 2 by 0.45 by 0.6 cos theta, and then we'll have two values. So we'll have LAB at 30 degrees theta. Okay, this is just going to be equal to LAB at theta equal to 30 degrees. This gives us, plug in 30 there, this gives us 0.45 squared plus 0.6 squared minus 2 by 0.45 by 0.6 cos 30. This is just going to be equal to 10 square root of that, and this gives us a 0.3080 meters. Then we have LAB at theta equal to 45 degrees. Plug in 45 there. We have 0.45 squared plus 0.6 squared minus 2 by 0.45 by 0.6 cos 45 square root of answer. So this just gives us a 0.4250. Okay, therefore L naught, because we thought the spring is unstretched, is just going to be equal to LAB at theta equal to 30 degrees, which is just equal to 0.380 meters, and L final will just be equal to LAB at theta equal to 45 degrees, and this is just equal to 0.4250 meters. So we have all the values, so we can calculate the value of Fs. The value of Fs is just going to be equal to K L final minus L original or naught, which is just going to be equal to 0.4250 minus 0.3080. So this just gives us a 0.117 K. Okay, so we have this value. Let's define these positions xb and xa and yb. So xb is just equal to xb is equal to 0.45 sine theta, and therefore del yb, this is now the vector displacement, del xb, del xb is just going to be equal to 0.45 cos theta del theta. Then we have yb equal to 0.45 cos theta. Okay, and then we have del yb equal to 0. minus 0.45 sine theta del theta, but I want the modulus. I want the absolute value, which is at 0.45 sine theta del theta. Alright, once we have this, then we can plug them in our equation. We know that our del u, which is the virtual work equation, is equal to 0. So plugging these, let's write down the equation. What do we have at b? In the y direction, we have both two cases. We have the first case, w is in the same direction with our vector displacement, therefore we'll have a positive vector work. So w times y del yb, then we have a minus, these are in the opposite direction, fs cos phi del yb. Then we have another negative in the horizontal. We have fs sine phi del xb, and this is equal to 0. So let's plug in the actual values in there. We plug in the actual values. Let me just create a boundary here. I create a boundary like so. Alright, there we go. What do we have? W, we already calculated it, is 245.25, and then times del yb. Del yb we said is 0.45, 0.45 del yb 0.45 sine sine theta, sine theta del theta. Okay, then we have a minus fs. Fs, why is it our fs? Our fs, we say it's just a 0.11. We are writing in terms of stiffness k, then times also del yb, which is just 0.45, 0.45 sine sine what? Sine theta. Okay, del theta. And then minus again 0 point, sorry, this one hasn't yet finished. It's fs, this is fs, fs sine, fs cos phi, and then we have del yb, which is just 0.45 sine theta del theta, and then we have minus again fs sine phi, and then we have del xb, and which is just a 0.45 cos theta del theta. So we can factor out the del theta like so, and then we multiply these numbers. We have 245.25 by 0.45, 245.25 times 45. So this gives us a 110.3625 sine theta, sine theta, and then then we have minus this other part, which is just 0.117 times 0.45. So this is 0.05265. Okay, I think the space isn't enough here. You can write it down here. 0.05265 cos phi sine theta, then minus 0.05265 sine phi cos theta. Is that so? And then this equal to 0. So we know that del theta won't be equal to 0, and the only part that will be 0 will be this part. Okay, so let's write that. So this is just a 110.3265 sine theta minus 0.05265 cos phi sine theta minus 0.05265 sine phi cos theta equal to 0. Alright, so once we have that, our task now is to find phi, because we know that at equilibrium theta is equal to 45 degrees at equilibrium, right? That's what they've told us, right? At equilibrium. So this is the final position, or the final, or the value of theta when the system is in equilibrium. So let's find phi. Alright, so therefore we can use sine rule. We can use this value now at theta equal to 45. We found that this is equal to 0.4250. So we can use that value, and we know theta already, so we just say sine theta divided by 0.4250 will be equal to sine phi divided by 0.45. Therefore, phi will be equal to, because we are plugging in this value here, this is the value that this system is going to experience or have when it's in equilibrium. Let's find phi. So sine 45 times 0.45 divided by 0.4250, sine inverse of that, we have phi equal to 48.48 degrees. So found this value. So we have all the values. So we just plug in this value here. We plug it also there. We also plug it there. We have also this value here which we plug there. Where we have phi, we plug it also there, right? So let's do that. We have values of phi and theta. We can therefore make k subject to the formula. This k. There's a k here that I was forgetting to write. There's a k here, okay? Sorry. There's a k somewhere here in between. I should have indicated a k here. There's a k here. Right. I don't know how. Yeah, there's a k there. So we can make this k subject to the formula, right? There's a k. This k here. How come there was a k here? There's a k here. This one here. This one. Okay. Sorry about that. Is that k that we just forgot to indicate. So we can make that k subject to the formula. We plug in phi and theta. Therefore, our k will just be equal to, which is the spring stiffness. The spring stiffness or the spring constant. This k will just be equal to, let's do the calculations, 110.3625 sine 45 and divided by 0.05265 cos 48.48 sine 45 plus 0.05265 sine 48.48 cos 45. This gives us a 1484.94 newtons per meters. Let's calculate again. 110.3625 sine 45 divided by 0.05265 cos 48.48 sine 45 plus 0.05265 sine 48.48 cos 45. This gives us a 1484.94. Alright, so basically this is our final solution. This is our final solution, which is the value, the spring constant. Alright, so I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.